Hello, everyone. I'm very happy to attend the P4 Summit. I'm Weiqiang Cheng from China Mobile. In the next 10 minutes, Professor Liu Jiang from Beijing University of Post and Telecommunications and I will demonstrate our P4-based edge router. It was developed based on open SRv6 platform. The presentation will have two parts. In first part, I will provide the overview of the solution. And in the second part, Professor Liu Jiang will demo our solution. And first, let's look at the background. As you know, cloud and edge computing are being widely deployed to support the growth of the new services. Operators need new networks to converge on the cloud, edge computing, and the various terminals. The edge routers will be an important part of the new network. Meanwhile, SRv6 is considered to be the key protocol for next generation carrier IP networks because it can provide end-to-end connectivity with simple and unified protocols. Therefore, based on the SDN architecture, the edge router that support SRv6 will be a very important product for operators. However, we might be a challenge to deploy SRv6 because the overhead is too heavy. Let's see an example. For some big operators, the traffic engineering path often has 10 to 12 hops. That means you need encap at least 10 IPv6 addresses in the SRv6 header. The figure here shows that the bandwidth utilization is even less than 60%. It's very high cost, as well the very heavy overhead also bring big challenge to the chip design. So at this moment, we raised GSRv6 solution. It can reduce 75% SRv6 header while supporting the full SRv6 functions. This kind of new requirements often happen. The header and the forward mechanism is different from SRv6. We should change the data plan. So at this moment, operators need the programmable data plan solution. To speed up the development of the SRv6 and the GSRv6, we launched the Open SRv6 open source project in 2021. Now, the first phase of the project have been completed, including an ODL-based controller, a Sonic-based operating system, and a programmable data plan based on the Tafino chip. We have developed an edge router based on the platform, which can support a full function of GSRv6 protocols. We also have done the field trial in Sydney network. The test result shows that it works very well. Next, Professor Liu Jiang will share the demo.
Hi everyone, I'm Jiang Liu from Beijing University of Posts and Telecommunications. I will take from here to introduce our implementation of P4-based GSRv6 data plane and the experiments. We implemented the core function of the GSRv6 with P4, namely using SRv6 or GSRv6T policy to support L3 VPN. The left image simply shows the pipeline of this GSRv6 P4 program, including the ingress and egress. In the right image, we show the layered architecture from the switch operation system perspective. We extended the P4 to SI to make Sonic support GSRv6 and correspondingly developed the API. Okay, let me introduce some details about this P4 program. The program functionally realizes the GSRv6 and SRv6. For the SRv6 function, we mainly realized the processing of the end seed in the intermediate rotor, and correspondingly realized the processing of the CO safe label in GSRv6. This P4 program is developed based on the BFSDE. The version is 9.2, and the program also follows the pattern defined in TNA, also known as the Tofino native architecture. This program is deployed on real P4 switches. The brand is Tradex. The ASIC is Intel Tofino. The capacity is 3.2 trillion bit per second. Here shows two images from the P4i, which illustrates the resource occupation and the table graph. This program occupies 11 stages in total, but the resource occupation is acceptable. For instance, the most occupied resource is the hash distance unit, but it only occupies about 33%. In this slide, we show the validation of the processing of the CO flavor in GSRv6. As shown in the left image, the capture result indicates that the program can encapsulate the GSID into the IPv6 destination address in order and update the segment left when necessary. In early experiments, we took advantage of the ONOS as a controller. Thus, we also reconstructed the P4 program to accommodate the regulations of the fabric TNA in ONOS, as shown in the right image. But after we accomplished the development of the SI, we transfer the controller application from ONOS to ODL. We also do some optimization in our P4 program to make it more efficient in SRv6 and GSRv6 processing. As we all know, P4 does not allow the cross-stage action in one-time pipeline. The dependency of the headers in the P4 program may occupy too many stages, especially for SRv6, because there is a strong dependency between SIDs. This dependency makes the program has a long pipeline and easily reach the limitation of 12 stages, and further limits the number of the SIDs that can be processed in one-time pipeline. Thus, in order to break the dependencies relationship between SIDs, we leverage the meta in the program for the non-active SIDs. This optimization makes the program can support processing 23 SRv6 SIDs during one-time pipeline, and ideally near 100 GSIDs. The final experiment was conducted based on CENI, namely China Environment of Network Innovations. CENI is an advanced experimental network across China. It covers over 40 cities, and the backbone link is up to 200 gigabit per second for now. The data plane of CENI contains both white box switches and segment routing routers, which can support different kinds of network experiments. The experiment of SRv6 and GSRv6 is deployed in Beijing and Nanjing in China. Across over 1,000 kilometers, we deployed two switches respectively in Beijing and Nanjing as a P and PE equipment. We applied two different routes from CNE, as shown in the green and blue in the left image. The experiment integrates P4, sonic, and ODL. The result validates the feasible and efficiency of GSRv6 in transmission, including the topology management and GSRv6-based L3 VPN. As shown on the right side, this experiment proves the concept of GSRv6 from different core functions. That will be all for our presentation. Thank you.